How many of you are familiar with Golang? Golang, about half, some shaky handsies. How many have heard more about Golang in probably the last year because of things like Docker or Openshift otherwise than the year prior? Pretty much everybody's heard about it before, since then. Golang, my name is Vincent Batts. I'm an engineer with Red Hat. I'm actually on the Openshift team. I would love to work on the Openshift code line, but I haven't touched it in about 18 months. I've been working exclusively on Docker upstream, contributing to Docker and containers in general. And so working on Docker upstream. At this point, I'm a core maintainer of Docker and have a couple of other container-related projects, and was actually using Golang prior to that, even at my prior employer. Before, I've been with Red Hat for 3 years now, and the prior employer was kicking around the tires of Golang because it has some really interesting advantages since it compiles the static binary and has very fast compile times. But since then, have brought some of that over to Red Hat as well in all the projects we've been working on. So Go, most people see it, and how many of you thought this was a gopher the first time you saw it? I've even got the shirt. Ooh. I'm sorry, that was loud. I've even got the shirt on that looks a little bit less like that one, but it's still the funny little beanbag looking critter with the big eyes and the teeth. You might have seen it and thought it was a gopher at all. No? It's okay. A lot of people have a lot of opinions about the Go gopher, and they think it's beavers and everything else, but it's pretty hysterical little cute thing from Rene French. The overview of the language is that it is a strongly typed language. If you've ever written in languages like Ruby or Python, that you could assign to a variable a string and then pop an int into it and it doesn't care. The Go programming language is a strongly typed language. It is a compiled language. It is not interpreted. And they have gone the extra mile on the stylistic sugar and otherwise that it does not feel like you're writing C. You still might have to deal with pointers and whatnot, but you don't have to feel like you're moving memory around. You can feel like you're writing something nice and easy like Python, but still have the performance of C. And it is very opinionated. And I think that comes with its heritage, and it delivers the point that the founding crew wanted to see in it, but it is an opinionated language. Despite the name of this talk, Golang, the good, the bad, the ugly, by and large, every single point that I'm going to address all the way through good, bad, and ugly, so many people will say, the good thing I thought was actually a bad thing or an ugly thing. And that ugly thing was actually pretty nice. Like it made something that was very difficult very easy to do. It might take a little bit to get your head around. But this is all just a very rough grouping based on my experience over the last years of watching other people come to this language and pick it up. And even if they picked it up very quickly and sometimes very, very difficult concepts, they said, well, it's still kind of ugly. And every time I need to do that thing, I have to go Google for the docs or the references to say exactly how do I do X. And sometimes that is ugly, but considering the difficulty of the item that they might have been working with, it still seems like it's pretty straightforward. So the good stuff, let's get into it. Fully qualified imports. Again, this you might have opinions on this already. When you go to import anything into Golang, you are fully qualifying where it came from. This is something that blows a lot of people's minds if they've ever dealt with Ruby, that you might require some library, and who knows where that actually came from. You might have gem installed it, and who knows where that actually came from, who the actual author was, where was it published. The gaps in the connection there. Sometimes with some languages, it's a little bit more clear, but it's kind of a framework baked into the language of where the import package path came from. It is expected to be a resolvable address unless you have overridden the fetching mechanism and just made the file source tree that the compiler looks for already there so it doesn't have to go fetch it. Otherwise, this has to be a fully qualifiable address. There's some baked in that it knows GitHub is going to be .git at the end, but you can specify your own repo by adding whatever it is .git, and then any paths back past that are slashes, and the compiler and the fetcher will actually go pull that from that fully qualified address, which is nice. It'll actually help you distinguish even within a project if you had, for any unfortunate reason, if you had remote libraries that you were using and some person forked it and added this feature, but you still need something that's over in this other one. I can't say that ugly things don't happen in code, but at least in this situation, they might have colliding names, but they still are namespaced by where they came from, and they might even be forks of each other. Really, really fast compiles. This is a trivial example for the typical hello world, but I'm from Alabama, so you're not going to get a hello world. You're going to get a howdy y'all. What you just saw there is it actually set up a temp directory. It did the full compile, got an executable, rendered it, and showed it to you, like right there. Sometimes people that are first, and there's actually in the command line tool, there's a go run command, like go build, go get, and otherwise. That you can be sitting in a source tree with all the stuff that you're hacking on and say, go run this or go run a file, and it feels like an interpreted language like Ruby and everything, like Ruby and Python, because it has already done the compile and it evaluates the static binary quicker than some interpreters can even load themselves. There's reports from companies, especially within Google, besides any stylistically pleasing pieces where they were able to take millions of lines of code and take them down to 100,000 lines of code. The big part for companies was if they had compiles of these incredible big stacks, frequently they would have to just keep them constantly rolling because they took about 12 hours to compile. And with the C++ code and doing constant re-inclusions of the same headers, and sometimes there were headers that were not even related to the project. And because they have to get pre-processed and pre-processed, some headers that were not actually in the resulting binary were getting re-included 32,000 times, and it's just incredible. They've taken their compiles from 12 hours down to less than 10 minutes. And there's a lot of stories about this. It's not entirely a reason to say it's a great language, we should choose it. But for many people, it's a big win. Good. If you were to look at this straight away, what would be, if first time you've ever looked at the language and you saw defer file closed, especially how many people are familiar with C? If you knew that you had just opened a file, you have open file handle, and God forbid you had an error anywhere in your code, but you always need to remember to close the file handle, you end up having a bunch of error handling logic or a go-to, something to make sure that no matter what happens for the rest of this code, and hopefully your functions are small, bite-sized, but no matter what else, I remember to close the file handle or the stream or the body or anything like what you're actually dealing with. So the defer call, and it's one of the built-in keywords of the language. It actually builds up a stack for whatever given function scope you're on. And as soon as you hit the end of that function, or if you had a return at any given point, these are showing log fatal, which would actually close the application. But if you were inside of a function and you had a return, because maybe you did the right thing or maybe you did the wrong thing, but no matter what, it would start popping off that stack of all the defers that happened to make sure I close any streams, I close any file handles, I reported a log to this other thing, and they're actually blocking operations. It knows that it needs to return. Those things need to happen before the person who called me actually gets whatever happens, but pop off the stack of all the deferred calls. Incredibly helpful in a lot of situations where you don't have if an error and then you have some itemized list of actions. It is garbage collected. The language is concurrent, and when it goes to run, it actually has a runtime that keeps track of the actual application, various pieces like the garbage collection. They've completely overhauled in Go 1.5 the garbage collection, and not many people ever had an application to where they ever saw a pause in prior versions, and they've almost gotten rid of that completely in the Go 1.5 garbage collection. But any Go routines, cleanup, we can get into Go routines in a minute, but it's convenient enough to where a lot of that for most, probably the 80 or 90% use case, don't even have to worry about what the garbage collection is doing. Yeah, so exports. There's no keyword around private and public functions within a package. When you're building out a library using Golang, if the variable function type is uppercase, it's exported. If it's lowercase, it's not exported. And so even in this situation, even in this library, the fields within this structure, BIF, are capitalized, but BIF is not exported itself, so you would not see those fields because the whole structure is not. But foo would be exported, and bar would be, but baz wouldn't be. So pretty simple process there without having to have additional keywords, remembering what you marked public and private. Or changing the scope of something midstream, like some languages, you could make something temporarily public and then, anyhow. Concurrency, it's baked in. A lot of the founding members worked on highly concurrent mainframe, whatever, all kinds of background stories on this. The type of concurrency they went with was from 1970s papers on channels and actually implementing channels without having to do a lot of the concurrency that folks in C++ world are familiar with. It is programmatically, it feels like a FIFO. You open a channel, you can give it a typed channel, you could even make it a buffered channel. So you could say you can have up to 10 ints in this pipe. Otherwise, it is a blocking operation to put in until somebody is ready to pull off the other side. So there's reasons for maybe needing it to be buffered or maybe just needing a straight channel. So in this situation, I'm going to start a table that is a channel that is just handling a type of thing, which is a ball. I've got two players that are going to interact with the table and let them play ping pong for 1 second. So you can see here the actual operation of the player. In production code, you might not want to have an unbroken for loop. This is just a while true. For any condition, just keep on running. But for a simple application inside a main, it will just exit after 1 second and take the ball off the table so that the routines don't have anything to work against. And it just runs. So it actually spun up on a single CPU by default. It will just start on a single CPU of a program. So it will spin them up in threads, but you can either, in the code itself, tell how many CPUs you want to use, like by asking the runtime, how many CPUs does this machine have, and you can set that kind of logic. There's flags that you can pass it at runtime if you've already got a compiled binary you're dealing with. But by default, without any manipulation, this simple main application is running on one CPU. It would just spin those up in additional threads or Go routines. The marshalling is pretty straightforward. The decoration looks like a little keyword. It's actually using backticks, but otherwise you can marshal most structures straight away. As long as it's an exported field, it will export it accordingly. And you can, if you're dealing with inputs and outputs to different types of like JSON structures that might need it capitalized different or otherwise, you can handle it. You can actually set the field name. But the marshalling, here I'm just taking a simple struct, putting it out to a raw stream of bytes, and then pulling it back into a new struct. And it's surprising how many times, especially some of the folks that have been on the team that come from the Java world where they're still dealing with XML files, there's an encoding package tree, and there's like PIM encoding, there's XML encoding, there's JSON encoding, and it's all handled exactly the same. You take something, they've got certain decorators for like you see the JSON and whatever the tag or field name, and for XML, there's some additional stuff of like, these things are actually nested 3 deep in this other structure and whatever. But your structures don't actually change, and you could just have the same kind of take it, marshal it by whatever the encoding we're dealing with, get something and unmarshal it back. So here, okay, so here I actually did that. I've left the same JSON tags. I don't even give myself any XML tags, but this time I'm going to be using the actual XML marshaller. And you can see that I start with a structure, main, my struct, my name, whatever. What happens in the middle is it just kind of renders XML, and then it brings it right back. So the marshalling has been a pretty funny one that you'll find yourself having to accommodate for somebody else's way of communicating, but all the structures can pretty much stay the same. You can marshal it over the wire. Easy learning curve is probably one of the most surprising, and to say good, that I've seen yet, because I've been on teams where somebody joins the team, they're plenty bright person, they've never touched that language before. You have to account for a month, 2 months, whatever, depending on the language and the particular team, for them to on-ramp onto whatever it is, how you do things. I've now been a part of a couple of different groups where somebody who's never written anything but Python, somebody who's never written anything but Java, and within weeks, they're already finding what's the overlap, what's the differences, how do I do it, and they're already writing code. Sure, it could use polishing, and maybe there's some more idiomatic pieces that it could clean up with, but otherwise, the learning curve has been probably the biggest plus I've seen for a lot of teams. Fast compiles, go-get is how you can otherwise pull in, if you were just sitting at your own code and you saw the fully qualified imports, if you just needed to build that, you could actually say go get dot slash dot dot, like anything in this tree down, and it would go and put that into your local source code path. There's like an environment variable for it in a tree, and it would actually pull the dependencies for the code that you're working on. But otherwise, you could see somebody's cute little project out on GitHub, github.com/vbats, like my cool thing. And if the source in that tree, or there's a path within that checked out tree that has the main application that's compiled, and it and all its dependencies have fully qualified paths, you can just go get vbats, my cool app. It will actually pull it down, all the dependencies, compile it, and put it in your path. And the very next thing would be the actual executable that you just were looking at wanting to do. Of course, for packagers, this makes them cringe, but for a lot of deployments, it's really, really fast. And most situations, even with the Git cloning and the compiling, it's less than a second for most projects. Cross compiles, this has gotten even more attention in the Go 1.5 release that will be coming out in the next months. But it has, since the beginning, supported Windows 64-bit, since the initial release, 1.0. Windows 64-bit, Windows 32-bit, Linux, ARM 6432, FreeBSD 32, 64-bit ARM, several different BSDs, Darwin, et cetera, et cetera, et cetera. They've taken a lot of, not a lot, they've taken a little bit of bootstrapping, but you could be sitting on your Raspberry Pi, pass a couple environment variables, and compile the same code again, and as long as you're not using platform-specific, like syscalls and stuff like that, for especially hello worlds and probably 80% of your use case code, you could be sitting on a Raspberry Pi, Linux, pass a few environment variables, and produce a 32-bit Windows binary .exe. You couldn't run it, but it would actually produce it, and you could copy it and deploy it, or Darwin, or so forth. For a lot of people, that's a very interesting use case. Like Openshift, we use this for providing, the daemon might actually need to run on Linux, but we can compile client binaries for OS X and Windows, 64-bit, 32-bit, and it's all from the same source tree. So bad. The things that actually stop you from hacking on things you want to work on. Packaging, this one has been frustrating, and I've seen far too much of all of this being at Red Hat. But because it's very easy to fork and have your little trivial application, the packaging right now, the state of affairs in like places like Fedora, It feels a little bit like Ruby and some of the other packaging again, because you have so many of them and everybody wants to have their cute little application. There's not huge upstream projects. It's a lot of individual problems solved. So a project like Docker and especially Kubernetes has hundreds of packages. It really is the time when people say, why aren't we containerizing the shipping of these things even easier? Because just the process of building RPMs is tedious, and I can still see the fully qualified, like what commit actually got used. I can have some of that assurance, but packaging is frequently a pain in the rear when it comes to all this. I hear a lot of people, mostly people from Java world, but a lot of people really complain about generics. There is not a clear notion of how that relates to Golang. There is a notion of interfaces, which is just something. An interface could be a string, it could be an int, it could be your structure. You have a way of doing a type assertion to say, are you like this int? But it's not generics. They introduced in Go 1.4 a way of generating code, almost like Yak or Mock or some of these other things where you could, on the fly, like when you go get it, because that ended up being the reason why some people couldn't go get code, is it actually needed to produce more code, and there needed to be an intermediate step there of rendering something that is like what you would do with generics. A lot of people grumble about it. The Go generate fixes a lot of those problems, but I think a lot of the folks that are just used to generics still are grumbling about this. I have never once said, I really wish it had generics. So that's that. Debugging. This is often the biggest pain in everybody's ass. When anybody comes up and asks, so how do you debug and know what's happening right here? Printf. There are ways of debugging it, and if you're not doing any concurrency at all, GDB might be able to help you. There's some Python wrappers that are provided by Upstream that can facilitate and like find the package name and help you print and see the lines of code that you're working on, step through it. But as soon as it goes concurrent, GDB is mostly useless. And even still, sometimes following pointers and following references and stepping through, it'll frequently bounce you back into runtime, and you're looking at assembly, and it's not actually what you want to be debugging. They have taken a few patches from Red Hat on, or have had good conversations about it. In Go 1.5, they've overhauled a lot of how the dwarf symbols are laid out to make it more useful. They're still saying that it'll probably be Go 1.6 before they spend the time focusing on that. There's been a couple of reasons in Go 1.5 that they were not going to give it bandwidth for that release. But it's something that Upstream knows most people complain about, and they kind of get a snobby remark from Upstream, not snobby snobby remark, where Upstream's like, well, just write good code. I was curious, is GCC Go any better with GD? There's some capacities that GCC Go will allow you to troubleshoot that a little bit better and use some of the same ELF utilities that people are familiar with for C and C++ compiled with GCC. I'm curious how that will continue to look after Go 1.5 is out, because one of the big things that they have gotten completed for Go 1.5 is now the Go compiler itself is completely written in Go itself. So it actually bounces a lot less across the C boundaries back and forth, and how they allocate stacks, and how the runtime actually will do memory mapping. A lot of things that bounce you down to an assembly and backup. I have a feeling that some of the tools will actually start debugging easier on Go, and you might be able to follow it further on GCC Go, but it's actually going to be a lot more in the old way the stacks were allocated. So most people are just trying to find however to figure it out best on the tools they have access to. It's not a good situation. This is less about concurrency in GC particularly. It's more about the runtime. And despite the hype about all kinds of projects, Rocket, Docker, otherwise, being written in Golang, it must be a really cool language because Docker's cool. Because of the runtime and because of garbage collection and there needing to be this kind of separation, and it's by the time you get to your main function, it's already concurrent. Certain things like set and s, fork exec, are not nice. You can fork exec something, but you can't actually set up the environment for the new PID, the namespaces, and so forth, and then exec into it. It's got to be one operation because from one step to the next, it might be in different parts of memory, so it has to send them all the way through together. And so due to the benefits of the concurrency and garbage collection, a lot of things like set and s are incredibly rough. You cannot do it within one PID, and so you'll find projects like Docker and Rocket to do operations like set and s and chroot and otherwise, they actually have to re-exec themselves. And it's made for a very funky pattern. I don't think it'll get, that piece of it won't get any better. But the garbage collection node, I've already talked about it. It's already gotten better, and it's never terribly bad for people. Yeah, fork exec, they're together. If you need to fork exec in your project, you might want to write that bit in C. But otherwise, if you need to split apart fork and exec, do it in C. But if you don't care and you're just basically executing something, Go might be fun. So ugly or just new and different. There are build tags. There's no if-defs. So if you've ever walked through C code to see how and what actually was produced, and yes, you might be able to like add -E to see how it pre-processed out. But otherwise, you're sitting there looking through how everything got evaluated, what was configured at the time that it actually built. And in Golang, there are build tags. It's a comment at the very top. It's like a decorator. And the compile, or there can be file extensions. So you could sit in a directory tree, and you might see syscall, or syscall _ Linux, syscall _ Windows. And it will actually, the compiler itself will look and know that if I'm compiling on Windows, I'm not even going to look at the Linux file. Otherwise, there's build decorators, what most people use just to be extra pedantic, that it's very clear. You open the file, and you can see that this code will only ever get compiled on Linux. Or for this matter, CGO, if it can't actually talk to C bindings, like a shared object, then don't even compile it. Pointer receivers. Don't really much expect, but if you were to look at this code and say, what is it going to do? I've got a message, which is just a string. It's kind of a stupid type def, but the message is going to write itself to some writer. That's fine. So if you looked at the actual main code here, I'm going to create a message of hello world. I'm going to write it to std out. I'm going to reset it, and then I'm going to write to std out again. What would you expect to happen? You'd expect it to write it once and nothing else the second time. So this is something that is ugly to most people, and they end up having to Google for it, and they Google and they have no idea even what they're Googling for. They're like, my function didn't do what I thought it did. I've got it reset right there, and you can see I set it to an empty string. Why did it not set it to an empty string? What the hell is happening to my code? And you don't know what you're Googling for, but it's actually, you're Googling for a pointer receiver. In Golang, this is a function of this type. This particular operation, anytime the signature of whatever the struct it is that you're dealing with, this is all in its own stack. It's a new pointer. It's basically a copy of m. So if you want to do something that actually modifies your m message, this current object, it actually needs to be a pointer. So you're actually working on the pointer itself. And without that, with just making it a pointer, so you know you're actually dealing with the original m, then it will do what you're expecting to do. But frequently you'll just see the code and you're running through and you're writing, a reset function and whatnot, and you don't actually know what it is that it's doing, and you set it somewhere, the value, you manipulated the original object or pointer, the original variable, but it didn't take. This is what a lot of people think is ugly, and sometimes you'll see just as a matter of habit, people always setting the pointer on it so that you're always just dealing with the original, because I don't want to forget that this thing's just a copy of the original. Just go ahead and work with the original. But you might have you might have use cases where you need to differentiate on those two. Pointer receivers are out there.
So this is just plain old pass by reference.
It's a pass by reference, yeah. Yeah, so if for the C pattern of taking a copy of something or passing by reference, this is basically just boiling it up into something that looks like, well, it's not really object, but you're basically passing by reference there, yeah. Underscore. Underscore is a special keyword or value within Golang, and it is a bit bucket. The language itself will fail compile if you ever instantiate a variable and never use it, or if you import from something and never use that import path. There's occasionally reasons for like the SQL implementation. You'll find this in a couple of different patterns where you might actually import the SQL calls and you will register some other library that's been used or initialized elsewhere. But when I'm statically compiling it, I need to have actually brought that code into my code base. So I never actually called that library, but I need it to be compiled in my main application. So you might occasionally see import underscore and then the actual full qualified path. So it included it in the compile, but if you included it and didn't use it, it would fail compile. Or sometimes during debugging, you might actually want to assign to a variable that you're going to use later, but you just want to printf in the meantime. You'll assign variable the output of something to a underscore. Most often that you see this pattern is you have multiple returns in Golang, and you might have something like a write operation. So I didn't actually put it out, but frequently you'll see a pattern like here. I don't actually care that, oh, gracious. I might actually care if I get an error here, and I don't actually care how many bytes I actually wrote in the operation, but you'll frequently see something like this because I have multiple returns here. I'm actually returning how many bytes I wrote and if there were any errors. And so when I'm actually going to call that item, I don't actually care how many bytes I wrote, but I want to see the error that I returned. So you can assign to the bit bucket over and over and over, and that's not strongly typed. You just can assign whatever to it. If you have any questions, do feel free to ask me at any point. It's just ugly, especially as people are going through and hacking. And if you knew that you had something that was returning an int and you're not actually doing anything with it, some very early people learning the language will end up like printf that integer that I got because I had to assign it somewhere and I had to use it after I assigned it, and so it makes for kind of ugly patterns when people have to assign to it and use it, but. That's why they made the bit bucket, because there are sometimes you've been given a variable that you need to do something with, and you can just drop it in the bit bucket. So that's why it's kind of ugly. It's not bad.
Going back to the pointer receiver stuff.
Sure.
In the first, I guess that's a member function. If we translate that to C code, you're really passing a single pointer, and in the second case, a double pointer, right?
Yeah.
Okay. Yeah.
Well, what you're working on is not the original, though. I mean,
you're working on a reference to the original, but in the reset, you're reassigning the reference and not touching it.
Yeah, that's true.
First example, and now you're
actually modifying the original. Yeah,
the original reference.
Correct. Yeah. Channels is something that are frequently ugly, and especially when you're first looking at it, just to see what is it that you're actually working on. The markup, most people have always dealt with greater than, less than, but the markup actually is a directional type pointer. So the actual channel marker is a greater than and a minus sign that looks like an arrow of where the data is actually going. So it's like a two-part operator that in this situation, I'm starting a go routine, so I'm spinning off something that will not be a blocking operation, an anonymous function. I'll step right past it. The code would go from assigning C, it would set up the go routine, and even as it's starting to evaluate for I and 0, I've already moved on to print line. Then I'll do a quick iteration from 0 to 9, trying to push that number onto my C channel. And then once I've done my 10 integers, I'm going to close the channel so it's not just hanging around. Closing a channel will make it up for garbage collection. So in this situation, it'll spin off and start working on that go routine, but this print line was actually just going to take the first one and the application ends. If I wanted to sit and wait for all of them, I'd have to like wait on it and select to see when the channel actually closes and other things. But still, the actual data pushing from I to C and then pulling from C out. And that marker is a little ugly to some people. It takes getting used to. This is one of the things where frequently people say, I think this is a situation I might need to use channels and otherwise. What's the exact syntax again? And they have to Google for it, like pointer receivers or anything. There's no enums, there's iotas. And iota can take all kinds of almost influencers. So, but straight away in this example, the disk create will be of task type, which probably something like an int. And the first one will be 0, and all the rest of them are 1, 2, 3, 4, and so on and so forth. And you might have situations where you see something that looks like this, but there's no 1. I go from 0 to 2. So you'd say disk create, and the second line would be an underscore because it's a bit bucket. The next line would be 2, 3, 4, 5, 6. You can find more examples of it in some of the lower level libraries, but if you said iota bit shift 2 positions, then each new line would bit shift 2 positions. So if you said iota times 2, then every new line would times 2 with the prior one. It's kind of interesting. Sometimes you actually have to sit and look at somebody's iota, and it's all within the single const. If you had the next line of another set of constant variables and you started a new iota, it would reset. So sometimes, depending on how magical the iota is, you might actually have to sit and look at it and say to derive what the value you're looking at is. But otherwise, some people think it's clean, some people think it's too magical. But that's what you get that's closest like an enum. For range, this is how you do most any kind of iterator. In this situation, I'm iterating over an array of strings for I, name, and range. It allows a little bit of magic so where the first situation, or this situation, you'll actually just get the position of the item in the list, so 0, 1, 2, 3, 4, or 0, 1, 2, 3. Anyhow, this one you could actually deal with the position as well as the value of that item in the list. And this one, I actually don't care what the position is. I just want the value, the name. Questions around that?
Yeah, can you name the bit bucket, like Kennen, Erlang, or
Name the bit bucket? No.
underscore, and then as long as it's part of the string?
Can variable names start with an underscore? I have no idea. But it wouldn't be naming a bit bucket. If it's allowed, then it would be its own variable. Bit bucket is special in that regard.
Is that a general multi-assign thing that you can steal the first one and ignore the latter ones? Like,
No.
it just applies to 4?
It applies to 4 and type assertion. You can actually say if it's like this thing, like you'll say if I is like an int, and it will return whatever you want that thing as an int to be, and a boolean of like whether or not it actually assigned to that or not. There's a few other magical ones, that's something that magical, like sometimes it returns 1 or 0 or 1 or more. That frustrates some people, that it should always just return 2 and you should deal with the other ones also. But it's special use case.
Arrays, are they more like Java or more like C in that what happens if I index like 6?
You'd get out of range. And so it's,
And then generate, is that true with memory manager in general? If I, like Java, allocate a byte array? Or
yeah. If you instantiate a map but don't actually allocate it, like you just say this variable will be a map, you'll get a nil reference that you're trying to insert something into a nil length map. So it's more like C in that regard. What am I doing here? Oh, so this is actually just iterating over a map. Map with a key of a string and the value of some structure that I've made called info. And so anytime you iterate over a map value, you get the key and the value. And just like an array, if you just said range over a map and I just only want one variable, the first thing you'd get is the key. It feels just like the position and value is now the key and the value on a map. One of the interesting other pieces that you can actually iterate on a channel. So like you saw, inserting values or pushing values onto a channel, now you can say for whatever on the channel and sit and read them and weep here. The actual code behind that is just, I've got a function that returns a channel with a type of a thing that's a card. And I push some of those onto the card, have a simple go routine. So in this situation, I'd call the function immediately, and it would get to right here and block and wait for you to start popping stuff off of that channel. And once you popped them all off the channel, then it would close the channel, and the whole anonymous function would get garbage collected. This is a dirty way of implementing an iterator, but it has its use cases. Interfaces and marshalling. This gets a bit into the weeds, but interfaces in this regard of Golang is you can actually duck type functions. You can duck type structures that behave like you want them to behave. Case in point, IO reader is an interface. It is not a special thing. You would not actually ever instantiate an IO reader. All it needs to be is any structure or any type that implements a .read of a particular function signature. So when you see something say, I take a stream like an IO reader, you could have your structure that just implements a .read function that matches what the IO reader interface says, and I can hand my thing to you, and it doesn't actually care what my structure is. They didn't have to import it. I didn't have to import your library at all. So unlike Java, where you'd actually say, this implements or extends, and I have to actually import your library, and it has to be present at compile time. They are completely separated. You just say you need that interface that it behaves in a certain way. I make my thing behave in a certain way, and if at some point somebody uses my code to hand to your code, it will implement the functions that your library or your functions need.
It doesn't have to be present at compile time.
Correct.
In Java, it doesn't.
Oh, okay. Well.
The implementation doesn't have to be present.
Yeah, runtime. Interesting. Okay, so I learned something.
So maybe I misunderstood. Does the interface have to be present for compile time?
Here?
Yeah.
No.
No, that's what I thought.
Oh, the interface doesn't even, you said the implementation of the interface, the definition of the interface has to be there, right? Because you're calling it. So it's got a signature or something.
So case in point, the FUMT format, FMT library, implements or has a definition of a stringer, and there's this kind of making a verb with everything, name or string or whatever. It implements a stringer, and it's any function that implements a capital string function that takes no arguments and returns a string. And so anytime you'd say FUMT print line or FUMT whatever, something that's just receiving an object, what do I need? Can I just printed out to the screen, it would first check, does it implement the stringer interface? So at the time that I wrote my library over here, I might not even import fmt, but I might go ahead and make a .string member function on my structure type. And then at some point, somebody goes to fmt println some instance of my function, it would say, oh, it implements string printed out. Neither the fmt library knew about my type, and my library never even imported fmt, but it happened to implement what it was looking for, so it thinks it knows how to behave with it.
So is this like a bit of mixing duck typing and templating, or?
It's more like what duck typing people kind of expect, I feel like. You still have to do type assertions, and it's less polymorphic than things like Ruby, where you kind of say, does it respond to .read and does it respond to .write? And then I guess I know how to operate with it. Most polymorphic languages that try and do this without too much magic have a big case statement of what it responds to. And this is just wrapping it all up into like a thing. So if you look through the I/O library particularly, most of everything in I/O is interfaces of like, it's a reader, it's a closer, and then you'll have another interface that's a reader closer because it implements both the things of a reader and a closer. And you can get these things that you know how to interact with and don't have to define them up front. And the reason I say marshalling here is occasionally I've seen shitty situations where you think you're dealing with an I/O reader and you go to marshal it out. There's nothing to marshal back. There's no fields involved. You're actually dealing with functions. And so if you go to marshal it out, you might actually marshal out what the real structure is. The fields might not even be exported, and you go to marshal it back, and you lose that. So that's the reason I put it on this slide. I don't know if I even have an example of that, but that part's ugly. You actually have to marshal real structures, real fields, not interfaces. Conclusions, despite a very somewhat slanted talk of this is not like rah rah, we should get excited about it. I like the language a lot, and I love it for a lot of reasons. It is surprisingly enjoyable to learn. I've watched now a number of teams, not only within Red Hat, but outside of Red Hat, companies like Bitly that had huge C code bases for certain use cases and huge Python bases because people just enjoyed writing Python more. They've been able to like consolidate and get rid of maintaining two languages and go to a single language and still have the performance that they were looking for. So it is enjoyable to learn and write and easy to adopt. But I feel like most any language, you should get familiar enough to where you like it and you're thinking that it's the best language and it suits all the use cases. It does not. There's plenty of reasons why you might need to choose or isolate use cases for a better reason, not just because the language is popular. So as long as you do that, I feel like you'll still have a good time.